abstract. So let us begin with a brief review of CR manifold. Today I call strongly pseudo-convex manifold simply CR manifold or pseudo-Hermitian manifold. And in this talk we always assume the manifold is closed, compact, without boundary, and the dimension is 3. It's known that on every strongly pseudo-convex manifold we have these structures: contact one form theta and almost complex structure on contact distribution and Lie vector field T. Actually, Lie vector field sometimes denoted by Xi, but here I want to use symbol T. Next, we fix local frame field because the dimension of M is 3, so we have this local frame. And using this dual coframe of cotangent bundle, we can define these partial differential operators. So A11 is a pseudo-Hermitian torsion, and subgradient and subhessian and sublapalassian are defined by this definition. And I think these are usual definition. And if pseudo-Hermitian torsion vanishes, M is called Sasakian. And finally, we use W to denote the Tanaka-Webster scalar curvature. Because the dimension is 3, the Tanaka-Webster curvature is just scalar curvature. Next, we define CR Panet's operator and CR Q-curvature by these formulas. CR Panet's operator is first order differential operator and consists of mainly square of sublaplacian and square of Lie derivative with respect to Lie vector field. This term is lower order term. Panet's operator and Q-curvature are originally considered in conformal geometry, and in conformal geometry these operators are considered as a generalization of Laplace operator and scalar curvature on two-dimensional surfaces. That is, if we consider conformal change like this, then CR Panet's operator and Q-curvature deformed by this formula. And this transformation law are quite similar to those of Laplace operator and scalar curvature on two-dimensional surfaces.
What is P0?
So P0 is CR Panet's operator with respect to this contact form, and P is CR Panet's operator with respect to this contact form, and this is same. It is by the definition of CR Q curvature, it is easily shown that the integral of Q curvature always vanishes. So if the Q curvature is constant on M, then Q automatically 0. So next conjecture, open conjecture or problem is just constant Q curvature problem. We consider
Theta 0 and lambda is what is
lambda is function on M. So this is conformal transformation of contact form.
Theta 0 is also one form?
Theta 0 is contact form, and theta 0 is contact form. So the positive multiple of contact form is also contact form. Okay. We consider three-dimensional closed pseudo-Hermitian manifold then can we find contact form such that Q-curvature vanishes? This is constant Q-curvature problem, and I want to consider in this talk. Here, I want to introduce some known result about Panet's operator and Q-curvature. Q-curvature and Panet's operator are originally considered in conformal geometry. So there are many results in conformal geometry, but today I introduce only this result, which is shown by Brayson, Chang, and Yang. We consider four-dimensional Riemannian manifold and fix a conformal metric G0. And we assume three conditions. First two conditions are conditions for Panet's operator. First, we assume non-negativity of P, and next we assume the kernel of P consists of all constant functions. And thirdly, we assume the integral of Q-curvature bound above by this constant. In this situation, we can always find conformal metric G such that Q-curvature is constant, this constant. If we consider CR analog of the CR version of this theorem, because the integral of Q-curvature always vanishes, this is a trivial condition. Instead of this, it's well known that the kernel of Panet's operator always non-trivial, in particular infinite dimensional. So this assumption never holds in CR geometry. For CR geometry, I introduce here this result shown by Professor Chan-Shu Chen and Chen and Chiu. In this paper, they introduced a Q-curvature flow like this, and under this condition, they showed the long-time existence and convergence of solution of Q-curvature flow. In this theorem, the assumption is essential positivity like this, and star condition I will explain later, and condition for kernel P, and condition for Q-curvature. Next, I want to explain this condition for Panet's operator. I remark that because of this condition, as a limit contact form, we can obtain vanishing Q-curvature in this situation. First two conditions are quite natural. So P is called non-negative if for all functions we have this inequality. This is inner product of phi and P phi. And next, because in CR geometry, this kernel P is always non-trivial. So we consider only functions which is orthogonal to kernel P, and we assume this condition, this inequality for constant epsilon, a positive constant. Yeah. Because we only consider functions which is orthogonal to kernel P, we use the word essentially positive here. Similarly, in definition 2, we consider functions orthogonal to kernel P, and we require this inequality. This condition is called condition star, and this inequality means we can estimate subhessian by this square of sublaplacian. In this inequality, this restriction of epsilon is quite important. Here, I want to state our main result. This theorem 3 is a generalization of previous work of Professor Chang and Chen and Chiu. Here we assume essential positivity, and here instead of condition star we assume essential subellipticity, and we consider this Q-curvature flow. This Q-curvature flow is a little modified from previous Q-curvature flow, but that modification is not important. In this situation, we can show that the long-time existence and convergence of solution, and if we assume Q0, the initial Q-curvature orthogonal to kernel P, then the limit Q-curvature of limit Q-curvature vanishes. And in proposition 1 and proposition 2, I investigated when the CR-Panets operator have subellipticity. And in proposition 1, if we assume condition star and this condition, these are used in previous work, then we can get subellipticity of Panets operator. So the theorem 3 is just generalization of previous work. In this talk, we consider this Q-curvature flow and the energy functional of Q-curvature flow. Because of this last term, R is defined by this. This is normalization term. Because of this normalization term, the volume V of M is preserved under this flow. Here, Q0 pop is perpendicular part, perpendicular to kernel P0. P0 is a CR-Panets operator with respect to initial contact form, theta 0. And if we consider energy functional like this, and flow like this, then it easily shown that this Q-curvature flow is a negative gradient flow of this energy. This means the first variation of energy functional E is always negative under this flow. Before to start the proof of proposition 1, I explain the condition star for P. This condition a little complicated. First, I recall CR-Bochner formula, integral version of CR-Bochner formula. This is also shown by Professor Chang. And this CR-Bochner formula relates square of Laplacian and square of subhessian. And because CR-Panets operator is mainly consists of this square of sub-Laplacian and square of the derivative with respect to the vector field. And furthermore, we can estimate sub-Hessian by sub-Laplacian. So, combining these three conditions, we can get this inequality. Here, rho is a curvature term, and alpha is a pseudo-Hermitian term. But these two terms are only these two terms are lower order term, including only first order derivative. So we can easily estimate these terms. And finally, we can get this inequality. And I note that in this inequality, by the restriction of epsilon, the right hand side we can take positive. Next, I show the proof of proposition 1. So here we assume the condition star for P and the condition for kernel P. Because sub-Laplacian is always sub-elliptic, using previous inequalities, we can estimate left-hand side below. So we can get this estimate of this norm. This SKP norm is called Hohenstein norm. And this is CR version of Sobolev norm. Please check abstract for definition of Hohenstein norm. And we can get the estimate of Hohenstein norm by inner product P lambda and lambda. After computation of commuter of sub-Laplacian and Panet's operator, using this condition for kernel P, we can finally get this inequality for lambda, which is orthogonal to kernel P. And because P is first order differential operator, so this estimate for first order Hohenstein norm is sub-ellipticity of Panet's operator. So this completes the proof of proposition 1. Next, I show the proof of proposition 2. By the famous theorem in CR geometry, the embeddability of M theta is equivalent to sub-ellipticity of box B Laplacian. On the other hand, by straight computation, we can represent CR Panet's operator by these formulas. Here, because S is lower order term, it's second order operator. It serves to estimate this first term to show sub-ellipticity of P. But by definition of CR Panet's operator, it's known that if function is orthogonal to kernel P, then function is automatically orthogonal to kernel box B too. So we can use sub-ellipticity of box B and box B bar for this function. So we use sub-ellipticity box B and box B bar. We get this estimate for function orthogonal to kernel P. And because S is lower order term, this completes the proof of proposition 2. Finally, I want to express the explain the proof of theorem 3, and this proof is similar with the proof of the previous work. There are two difficulties to consider this problem. First difficulty is, as I mentioned, the kernel P is always non-trivial. And second difficulty is P is not elliptic in general. To avoid second difficulty, we assume the sub-ellipticity of P in this theorem. And to avoid first difficulty, we consider the decomposition by this direct product, direct sum. Yeah. Using this decomposition, we decompose the flow like this. Here, lambda part means the orthogonal part of function lambda. And lambda kernel means the kernel P0 part of function lambda. And this is similar. This. So for this decomposition, we only consider P0, not Pt. Using essential positivity of Panet's operator, we can show this estimate. This is constant depending only on Q0 and K. K is here, and epsilon. This is used in essential positivity. And using essential sub-ellipticity of P0, we can estimate below this term by this. Finally, we use CR version of Moser inequality. We can show that this value, this is mean value of function lambda, bounded below constant by constant. So combining this and this, we can get this estimate for Hohenstein norm. This is a priori estimate for the solution lambda. Next, I show the long time existence and convergence for solutions. First, we deal with this second equation. Because the right hand side of this equation, RT, the variable of this function is only t, only time t. So we can use contraction mapping principle for this equation, and we can get long time solution lambda kernel. On the other hand, because we assumed non-negativity, so essential positivity implies non-negativity. So we assume non-negativity, and also we assume sub-ellipticity. We can get short-time solution. And we use a priori estimate and Sobolev embedding theorem, Sobolev time embedding theorem for this Hohenstein norm. We can get long-time solution for this flow. Next, we show convergence of solution. To show the smooth convergence, we compute second variation of energy. And it can easily shown that this second variation always negative. And this implies the limit of this integral vanishes. Because this integrand is squared, so we can get this and this relation. Next, we compute the energy of a little higher order. So this is energy a little perturbed. And after estimate of this quantity, we can get this integral is infinite. Using this relationship, we can easily show that this inequality. So this infiniteness of integral means L2 convergence of solutions. Next, we use similar argument with this. So using essential positivity and essential subellipticity, we can estimate this term from above. So using a priori estimate and the Sobolev emitting theorem, we can show smooth convergence of solution. This completes the proof of theorem 3. Finally, I want to talk about next open problem, and some applications for these theorems. First, I want to talk about application of today's theorem 3. The statement of theorem 3 like this. Other application of this theorem 3, it is well known that corollary 1. It is well known that if Hermitian torsion A11 vanishes, it means Sasakian. And it's known that Sasakian manifold is embeddable. So using this, any Sasakian manifold and we assume P is essential positive, and moreover we assume Q0 belongs to, Q0 is orthogonal to kernel P0. Then we can show long time existence and convergence. Moreover, because of this assumption, we can show the limit of Q-curvature vanishes. Corollary 1. And it's also known that if Yamabe constant of CR manifold positive and Tanaka-Webster scalar curvature positive, then it's known that shear Panitz operator is essential positive and M is embeddable. So applying theorem 3 and theorem 2 in this situation, and we assume Q0 belongs to orthogonal part, then we can show same conclusion. Moreover, this condition and this condition for Yamabe constant and scalar curvature is open condition. So we can apply this theorem for the manifold. So a little part of the manifold of this kind of manifold. So this is open conditions. So we can part up a manifold a little bit, and for this manifold we can show same conclusion. Next, I talk about next open problem. First, I want to consider generalization for higher dimensional manifold. In this case, could you turn off the light? In this case, the definition of Q-curvature for higher dimensional manifold is a little complicated. It's very complicated. So this is a difficulty to consider this generalization. And I want to consider this prescribed Q-curvature problem. This result is shown in conformal geometry. So for conformal manifold, we first give a positive function. Then they showed there is conformal metric such that Q over F is constant. This means Q is proportional to original function F. This kind of problem is called prescribed Q-curvature problem, and I want to consider CR version of this problem. This is all of my talk. Thank you for attention.
Are there any comments